Hello, welcome to GIS Day. I am Keshav Bhattarai. Professor Buddhi Gyawali of the Kentucky State University. He called me and asked me if I will be willing to give a talk on the GIS Day. Actually, I started my career from Eastern Kentucky University, located not far away from this Frankfurt, and I felt very honored, and then I accepted this talk. In this short video, I will present what is GIS Day, why GIS Day started, and then I will also talk about what makes the GIS so special that other science cannot do, and we have been emphasizing on the GIS Day. And then after that I will talk about the application of GIS. In that application of GIS, and I will use simple global positioning system, the application of the global positioning system that we have been using day to day. And when we go from one location to another location, so now we use GIS, the GPS, global positioning system. And is that some relevant to this one? And so I am presenting it and how the theory of the global positioning system is working based on the GIS. And then finally I will present the take-home message. So my talk is at the Kentucky State University, that is the Frankfurt. So why GIS Day? GIS Day started in 1999 as an educational event. GIS users are finding this event an effective platform in disseminating the concept of spatial sciences and applying this concept for real-world solution. It has opened the door to schools, business, and public. In the businesses, and the crime mapper, surveyor, engineers, computer-aided drafting, geographer, agriculturist, and the forestry management. Forestry manager, urban planners, a demographer, many are finding useful this GIS software. And as a result, the GIS users and the vendors are demonstrating the benefit of the GIS to make a difference in our society today. So actually that GIS Day did not come in one day. It started from long back ago, and in the 1960s. The concept of geographic systems started. In 1963, and Roger Tomlinson, who is also considered the modern day father of geographic information systems, and he started his the applications of the GIS from Canada, from the cadastral mapping to forestry applications to a varieties of applications where he store the varieties of the data in the computers, and then display those data, retrieve those data, and manipulated those data. And since that time onwards, the GIS has been used extensively in various applications. In 1965, a group of people established a computer lab in Harvard universities, and then they also developed a SciMap, one of the mapping project. In 1969, one of the members of that the Harvard laboratory, Jack Dangermond, and his wife Laura, they went to California and they established the ESRI, Environmental System Research Institute, and which today has advanced many features in geographic information system that the ArcGIS what we use today. In 1981, more powerful computer evolved, and with the evolution of the computers, GIS has integrated a lot of computer programming into it. And I will talk about that and how that computer programming are included into it. And a variety of computer mapping and spatial analysis has been possible today with the integration of the computer programming. Looking at the evolution of the GIS, first it started with the ArcInfo, that was the command driven, and we have to write the commands and the prompt, and then we could retrieve the data, and we could modify the data, then we could make the map. But today we have the window driven, that is ArcGIS 10.1, 10.8.1, and also ArcGIS Pro 2.6.2. Professor Bhattarai has received a lot of grants, and he has all this modern software here, and he has made this lab, Kentucky State University, as the state-of-the-art center. And so it is the right place to come and learn GIS. And so why people use GIS is because ability to create their own digital map, and that they could make a varieties of the layer to solve the real world problem. And it has been a good platform to share data and research collaborations. And it has helped to uncover all the hidden mysteries and what is behind my house and what is in front of this Kentucky State University, and what is there on the right hand side, what is there on the left hand side, and what is in the north, and what is in the east, and what is in the west, and what is in the south, like this. And with the evolution of the web-based cloud computing, and it has been enabled GIS to use the Internet of Things, IoT, and which is used to develop the smart cities. Today's the urban planner. They do a lot of work with the GIS, and they utilize that to develop the smart cities. And I will talk about that smart cities and then how we have integrated this into our life. And I will give you an example of simple the cell phone that we use. What makes GIS so special that other science cannot do it? And so first thing, it helps to locate the particular locations. The concept of locating a particular place did not start evolve in one day. That started from the 3rd century BC by a Greek geographer Eratosthenes, and he developed that, and he imagined that the earth, how about that earth has some imaginary lines going east and west and north and south. And then later on, Hipparchus, the Greek astronomer, between 119 and 120 BC, and he actually showed the practical demonstrations of the latitude and the longitude. And the people were confused, and which one comes first, latitude or longitude? And then there's an LAT that starts first, and the LONG that starts later, so therefore the latitude would come first and longitude would come second. So here I have collected some of the data from the compounds of the Kentucky State Universities, and where I have noted that latitude comes first and the longitude comes second. And in the longitude, and it has the negative numbers. And how to solve that negative number, I will tell you in a few minutes. And since it has the geographic coordinates, latitude and longitude, that is called the spatial data. And then this information here, about the Kentucky State University, we could gather that in a table, in a piece of paper, in a Word document, in Excel, and we could do that. That becomes the descriptive. And that does not tell us, and it will tell us where it is if we are very close to it. But if we are in South America, if we are in Africa, if we are in Asia, and if we are in the European countries, and where that Kentucky State University is, and we would not know that. So therefore, that the latitude and the longitude helps with the description here, the description, and then when we join them together, that forms the spatial data, and that helps to locate a particular location. That is a very special thing that GIS would do. But is it easy to do that? No, it is complicated, and so the complicated things have been simplified by the GIS. How? Is that the Earth is spherical. That means it is tapering on the polar areas and widening at the equatorial areas. And if you look at those the spaces, how the longitude and longitudes are spaced apart, they are widely spaced at the equator, and they are narrowing towards the pole. So that makes the distances between these two longitudes different. But here, if we look at the latitude, they are almost equally spaced, but going to the polar areas, that is a flat, that in the flat areas, and we take a long leap. And so therefore, they are a little bit widely spaced. So, but they are not that much widely spaced. So longitude, the spacing of the longitude makes very special, and so this is why the GIS science, it is the only GIS science that takes into this account, and so therefore it makes it very important. So what is the use of latitude and longitude? Actually, 1 degree of latitude is approximately 364,000 feet or 69 miles. And 1 minute equals to 6068 feet, 6068 feet or 1.15 miles. And 1 second equals to 101 feet. And so a longitude determines the measuring. In longitude and the latitude, they are measured. The values of the latitude and longitude are found from the cross sections of those two lines, that is the longitude and the longitude and the latitude, the crossing point is the angle. That is the angle that gives the particular locations of a place. And so 1 degree of longitude equals 288,254 200 feet or 54.6 miles, and 1 minute equals to 4,800 feet or 0.91 miles, and 1 second equals 80 feet. So for example, so what I am giving you here, that I was standing at Louisville, Kentucky, and I was also standing at Frankfort, Kentucky. And this is what the latitude I got for Louisville, and I got the latitude for the Frankfurt. And then I found this website here, and you will see this website here. And in that website, and I plug in the values of Louisville, and I plug in the value of the Frankfurt, and then I got the distance of 40 miles. And you might be telling that, is this only 40 miles? No, it is a crow fly distance. That means directly it came there from Louisville to Frankfurt. But I will show you, and you might be asking me that you told us about the use of application of GPS, and the GPS takes the route along these roads, the distance along these roads, and how do you measure it? And I'm going to demonstrate that in a few minutes. Okay, so this one you could see that is how the locations of these, how the spacing of the longitudes are, and how the spacing of latitudes are. And these are, they cross each other, and they form the angles, and which is called, determined by the Hoover sign formula. And you have studied that in trigonometry, and also in mensurations, and in dynamics, and you study that. And so in that, earlier I told you about the negative values here. You see that negative values here, and then how do we make that negative values to positive? And so here, this is the spherical Earth, and this is the prime meridian, and this is the equator. And so what is there? All the values of the latitude, they are located in this quadrant, becomes positive, and all the values of the latitude located in this quadrant also become positive. What does that mean? Any values of the latitude and that are located above the equator, they are all positive. They are all positive, or represented by N, the north. And all the values of the longitude, however, that are located west of the central meridian, they are negative. That is how we are getting these negative values here. These are negative values because United States of America is located in this sphere. So any values of longitude that is located west from the central meridian, that becomes negative. Any value of the longitude that is located in the east of the central meridian, that becomes positive. And then with that, and we have to make them positive. And how do we make them positive? That is the GIS science helps to determine the length, to determine the distance from two places, because we never ever travel negative distance. And for example, 40 miles I showed you from the Louisville to Frankfort, Kentucky, it is not negative 40 miles, but it is 40 miles. And how do we make that 40 miles? I'm going to tell you that. Now, negative degrees values are turned into positive numbers, and how we do that? The angular relationships gives the angular degree, that is the latitude and longitude. This latitude and longitude have to be converted into the positive numbers, because the Earth has the value of the latitude ranges from 0 to 90 degree to the north, and 0 to 90 degree to the south, and these are represented as S, or these are represented as N. And the value of the longitude, they are either 0 degree to 180 degree, because the Earth makes the 360 degree, or it makes the 0 to 180 degree to the west. And so 180 degree to the west, 180 degree to the east, that makes 360 degree. That is what about 360 degree. In one day we have 24 hours. So in 24 hours, and what happens is that in order for the sun to travel from 1 degree to another 15 degree, that will take about an hour. So that is what about the 15 degree. The 15 degree longitude, and we divide the 360 by 15, that makes 24 hours. And does that apply the same thing apply to everywhere? No, because the distance between these two longitudes are very closely spaced, and whereas at the equator they are spaced widely. So therefore, the only GIS science can solve this mystery. Other science cannot do. This is why we celebrate that GIS day. And so how do we do that? And in order to make these negative numbers positive, the French mathematician Descartes postulated a theory of the Cartesian coordinate system. And with that Cartesian coordinate system, this is made the equator, from the equator to the north and the equator to the south. And he made everything flat. The map, the circular map, has been made into flattened. And once it is flattened, and then everything was measured in the metric system. Instead of the degree decimal, everything was measured in degree, in the measurement unit like miles, kilometers, meters, inches, centimeters, or feet, and like this. But with reference to everything here, with reference to this. And so we have seen that in the Kentucky State University, when I came here, and I found that this road north of this north and then south, and what is the north and the south? And we are not at the equator, and why they are north and south? They are taken with reference to a particular location. With reference to a particular location, for example, this area is north from here, and actually equator is here, and everything is north here, but this area is considered as north from that point, and this area is considered south from that point. And so with that, what we have done is that we have made that false easting and a false northing in order to make these negative values positives. And we ate a very large number, like 500, 5,000, 1,000 numbers, in order to make these negative numbers positives. And here you could see that latitude and longitude. Latitude are positive, and because they are located above the equator, so therefore there is no problem. But in order to make this longitude positive, and how do we do that? And we have to make certain assumptions, and to make these assumptions, so what do we do? And what is my height? And for example, at this time is 5 feet 4 inches. And if I wear heel shoes, and then I become taller. And so that means my height has to be measured along with the shoes, the heel of my heel shoes, the high heel shoes. And so to measure that, and geodesy, and these are the engineers and who know the in and out of the Earth's surface, that the Earth's surface in the interior area is not uniform, so it is a zigzag one, and so sometimes it is going down and sometimes it is going up. So therefore, in order to take the center of the Earth has been divided into several zones. And for example, in Universal Transverse Mercator, they have flattened the Earth systems and they divided that Earth into 60 zones, and dividing that 60 zones, that means the 360 divided by 60, that makes in every 6 degree there is one zone here. Every 6 degree there is one zone. And so in the United States has 8 altogether, there are 10 zones, and it is divided into that. And based on that, and they have found the center, with reference to that, they have projected the map. With the projection of the map, and they would use that particular number 5,000 or negative 5,000 in order to make that negative value positive, and remain within that positive values. And for example, here these are the longitude values, these are negatives, and these negative values have been converted into positive values, and by adding those numbers here. But these numbers are added with reference to a particular location, the particular locations, and then they are made positive. And so this one shows that still that in the cadastral survey, when people have to measure the land, and because these lands are very, very valuable, and so therefore they have divided that United States of America into 120 pieces, and they have found 120 centers. And from that 120 centers, and they have found with reference to that particular locations, they will project it. For example, the Kentucky is projected to the north, Kentucky is Kentucky North and the Kentucky South. So they have projected it. And so these are called the projections, and the science is called geodesy. And that only the GIS can incorporate those type of the facts. This is why GIS is so special. And also, the very specialty of the GIS is that it can incorporate the real-time data. What does the real-time data means? That in some places, and if you are using the cell phone as the GPS, it will show that road as a red line, and in some places it will show the green line. What does that mean? The red line means there is some accidents, there is some traffic, and how does that get it? And in the TV, you have seen that Doppler radar that collects locations from place to place and a lot of locations. And these locational data, the spatial data, are incorporated into GIS. And then in the road, every segments of the road has the geographic coordinate system. The car goes from one location to another location, another location to another location, another location to another locations, and when it goes there, it crosses the distance at the same time, and it also spends some times. And this distance travel is tied to that time. And on the background of the computer, on the background of the GPS, a program runs. A programs continuously run. And when we move from one location to another location, we put the coordinates of that destination, and then the GPS would calculate your ETA, estimated time of arrivals of that particular locations. And how does it do that? It takes the geographic coordinates and then converts that into positive number by adding the large number. And all the programs is going on the background, and we don't see that background, but it converts that into human readable format that everybody can read it. And so this is how the Cartesian coordinate system has helped to use the global positioning system GPS and has made our life much simpler. The concept of the real time is also goes back. The history of the real time data integration goes back to 1660 when Sir Isaac Newton, and he discovered the theory of the gravitational force at that time. So what he found is that on the equatorial areas versus the polar areas, the gravitational force differs, and many of you must have read this formula: F gravity equals m times g, and that is mass times the gravity. Based on that, and there is a more friction at the equatorial areas and less friction towards the polar areas. And so based on that, and so what is the speed limit of a car going from one location to another locations, and how much time it will take to reach? And based on that, the GPS will tell you about the ETA, estimated time of arrivals. And that also communicates, the GPS also communicates with the satellites that are located at a very far distance. And I will tell you about that, and now you might be telling that, I am telling all this about these roads, but this land surface is continuous, is a continuous surface. And how do you map that for the continuous surface, and if there is uphill or downhill? And so how do I do that? And to do it, and so these days the GIS has been made so simple you cannot imagine it. Let's say that this is a Google Earth. In the Google, you open the Google Earth, and when you open the Google Earth and you click the terrain at the bottom there, on the left hand side, you need to click the terrain, and otherwise if you click a different location, you will not see the elevation. But you will see the elevation once you click the terrain, and then like the sketching, draw a line like this. Click, draw a line like this. And then after that, and there is a website called the GeoVisualizer that generates the elevation. And then you input that line into this, and then that will generate the points. And when the points are generated, and what happens that there are some spaces in between. So these spaces, we cannot get the points for every location. We cannot get the points. So therefore, we need to interpolate. And then GIS has the capacity to get the values of these points, and then get the average, and then fill the gap here. And once it fills the gap, and it creates the continuous surface that is called the raster surface. And then with that raster, you could see where the elevations are and where the gorges are. And then that you have seen that in various maps, you have seen the contour lines. And these, if you want to show these, so a very simple map with the contour elevation, and just put those contour lines here. And then if you are not still interested, satisfied with this, and those are the engineers, and who have to find out the cut and the fills, to cut so much of amount of the soil, it will cost so much of money, and they have to make the estimate. In order to do that, and what they do is they draw the triangulated irregular network. So what does that mean? If the plain area is there, and so that means that will make the bigger triangle. If the area is undulated, that is up and down, up and down, and up and down slope, and that will make the smaller triangle. And so therefore the engineers would make the different types of the estimation. So this is why engineers find that GIS a very special tool. So here, based on that, and they have made these, they draw the road lines, and where what the roads are, and they take the pictures first, and then they draw the lines, and following that line, and they will find out then what is the elevation from going to this place to that place. And first they will calculate how much is the speed of a road, and then what is the elevation, what type of the gear the car has to put, because going to the uphills and it will consume more gas. And so therefore they will also, the transportation modeler also use this GIS in order to make the transportation modeling, and then sending goods from one location to another locations and another locations. But that too depends upon what type of the images they are using. And if they are using the very coarse images taken from the very high the elevations, so that means that the image is very coarse. And if we are taking the pictures from a very short distance, and the pictures becomes very, very sharp. With that sharp picture, and we could get everything very close. And with that very bad pictures or the coarse resolution, poor picture, and we draw the road a jagged here, jagged. The car would go this way, that way, that way. And so these are the lines that are drawn earlier in the 1960s and the 1970s in the United States. And you will see that these maps were drawn from the Tigers files. You will see the Tigers files. What is the Tigers? It is Tigers. It is not with the class tiger that goes to the forest and that roar around, but it is the topographically integrated, geographically encoded referencing system. These are already built into the GPS, and that is the GIS. GIS is behind that theory. So this is all about, and I told you about the applications of the GIS in a nutshell. And first I told you about the GIS day. Second, how the GIS day was evolved. And the third, I told you about what makes the GIS so special. And the fourth, I told you about the applications of the GIS. And then in the GIS, and it uses both the vector data and the raster data. Vector data means the line, point, and the polygons, like this. And these are called the discrete data because they do not cover the continuous surface. And then I told you about the raster data that also forms the continuous surface. And these continuous surface, how they are derived. And these days the GIS has been very simple, and using just the Google Earth and drawing the lines and using the geo visualizer, and we could convert that into a continuous surface. We derive that raster surface, and then finally we make the map. And then there are a lot of applications about the GIS. GIS, for example, transportation modeling, crime mapping, agriculture, the precision farming, the computer-aided drafting, the engineering, and the forestry management, and so on and so forth. And even the communications. The communications, they use how tall should be the antenna of a particular location, and because the high frequency, low frequency, and so how they are transmitted, and they need to see the line of sight from only some of the lines, like the high frequency, they could transmit from the high frequency. You know that the antennas of the TVs are erected on the top, and they are not at the floor. And why? It's because the rays goes through the line of sight, and this GIS can help to determine those locations. And this is all about the application of the GIS I wanted to tell you, and it has become 28 minutes, so the 28 minutes and 30 seconds. I would like to stop here, and one more time I would like to thank Professor Buddhi, and I hope he will be able to build the science and then disseminate the information of the spatial science at the schools and the community level. Thank you very much, and have a nice day, and have a good GIS Day 2020. Thank you.